Yesterday, we drew a picture on the board of an object moving towards another object that was at rest. They collided, they stuck together, they headed off as one object because of glue or sticky tack or whatever the case may be. We analyzed that yesterday and a number of times over the past week by simply saying PI is equal to PF. That's a pretty straightforward question, right? PI is equal to PF. We could technically analyze it using impulse if we analyzed only object 1 here and not object 2 as well. When we're analyzing one object, it's impulse. When we're analyzing the system, then it's going to be conservation of momentum. Usually in these cases, it makes sense to do conservation of momentum. We'd say in this case here, M1, V1 initial plus 0, because the initial velocity of the second object is 0, equals MVF, M being the combined mass if they've stuck together. If they didn't stick together, then we just have two terms afterwards, right? M1 V1F plus M2 V2F. Right? Good? Right, we're good with that. We've been working on that for a week now, and we're good with that problem. Let's try another one. Let's say object 1 is at rest, object 2 is moving downwards from the top. We know how to analyze this one as well. It's pretty much the same thing as the first one was. PI is equal to PF. Well, this time, instead of saying M1 V1I plus 0, we're going to say 0 plus M2 V2I, because this time it's the other object that's at rest. It's object number 1 that's at rest instead of number 2. The final momentum is MVF, the combined mass times the final velocity. In both cases, we're probably going to solve for VF, although it's conceivable that we could have to solve for a different variable other than VF. Now, the problem that we encountered yesterday was when we have object number 1 moving at a certain speed to the right and object number 2 moving at a certain speed downwards. They collide right here. They head off as one object somewhere down and to the right. How do we analyze that? Well, we said yesterday we have to basically turn it into two problems, an X problem and a Y problem. Our X problem, the good news is, the X problem is this. That's it. All there is to it. M1 V1I plus 0. Still 0. Why is object number 2 why does it have a 0 momentum before the collision here? Yeah? Because it's not on the x-axis. As far as we're concerned, it's at rest when we're analyzing the x-axis only. Similarly, when we're analyzing the y-axis, we're going to use this. This time we've said object number 1 has 0 momentum. But wait a second, it doesn't have 0 momentum. It's moving to the right. Why did we say it has 0 momentum in that problem? Well, because we're analyzing not to the right or left, we're analyzing the up and down component, the y component of it. Once you solve for VF x component and VF y component, then you combine them. You guys remember how to do that? Remember how to combine them? Here's the x component, whatever we got it to be. Here's the y component, whatever we got it to be. And then we're just going to combine them using the Pythagorean theorem. Theta is found by measuring the angle at the beginning of the diagram, and then V is found by doing the Pythagorean theorem. Does that ring a bell? So now you got one more thing to think about when you see a problem. And it's not just these problems. It's not just conservation of momentum in two-dimension problems. Okay, every time we see something now, we want you to be thinking about what's the concept. We want you to be thinking about circling things in red. We want you to be thinking about what we know, the general ideas that we know, the bigger picture. But we also want you to be thinking now when we see a problem, if it's involving a vector, that is, we want you to be thinking, is it one dimension or is it two dimensions? Is there an x-axis or a y-axis, or is there an x-axis and an x-axis, a y-axis? Okay, if it's one dimension, all right, great. Do it the way you've been doing it. If it's two dimensions, x and y, then you've always got to break it into the x and the y. All right. We had a few questions for homework last night. First set we had was page 492, I believe. Yeah. Any issues with either of those questions on 492? All right. If we don't have any questions with 492, how about the questions on 495? I'm going to take a wild stab at this and say that somebody out there may need me to go over question number 2. Is that correct? Okay. We'll definitely go over number 2. It's a challenge question right now. This time tomorrow, it shouldn't be a challenge question for you. Actually, it should be, hopefully, relatively straightforward. But at this point, it is, because I don't want to say we haven't done it. We have, but we haven't. Okay, this is putting a few things together that we've done this year in Physics 30 and combined with a couple of things that you did back in Physics 20. And I wanted to see what you could do with that, to see if you could combine those things yourself before I went over it with you. Listen, if you couldn't, don't sweat that. That doesn't mean you're going to fail Physics 30, okay, or even do badly in Physics 30. Okay, it was a challenge. Okay, and if you didn't get it, that's okay. We're not always going to get those challenge questions. All right. Is there anybody for number 1, or are we good with just number 2? Yeah? Okay. Let's draw the picture for number 2 first. It says a 65.2 kilogram student on a skateboard is moving to the west at 0.4 meters per second. All right. That's what's happening before anything takes place. We got let's call it mass object 1, 2. Because it's object 1 and object 2 combined, right? It's the guy and the skateboard together before anything happens. His mass, or the mass of that system, is 67.7 kilograms, and the velocity of that system is 0.40 meters per second to the west. All right, that's what we've got. Then he jumps off the skateboard. So he goes one way, skateboard goes another way. That's like an explosion, right? When you fire a gun, the gun goes forward, backward, you go forward, or the bullet goes forward, the gun goes backwards. When a bomb explodes, and one piece goes this way and one piece goes this way. When he jumps off, the skateboard is going to go one way. He, however, we're going to make this the point where he jumps off. He's going to go, we already know he's going to go, object number 1, he's going to go 30 degrees south of west. Object number 1, by the way, the guy is 65.2 kilograms. And he's going to be moving at 0.38 meters per second. Where's the skateboard go? Where's it go? Yeah, it's probably going to go up here somewhere. Its mass is 2.5 kilograms. We don't know what its velocity is. That's what we're trying to find, right? Hey, it tells us to ignore friction between the skateboard and the ground. What are they really telling me there? They're telling me in simpler language to pretend that this is an isolated system, right? You know what? We probably would have pretended it was an isolated system anyways, even if they didn't say that, right? We probably would have done that. They're just confirming for us that we can do that. All right. If you were in my Physics 20 class last year, you might know the answer to my next question. If you weren't, you, at some level, know the answer to the question. It's just that you haven't heard the question phrased this way before. So you might not know the answer right away. Okay, especially my guys here. Okay, answer this question. When I see this problem right here, okay, beyond the 2 dimensions that we have here, beyond the conservation of momentum concept, okay, beyond all of that stuff, when I see that picture, a certain phrase should come to my mind. What is that phrase, Michael? No, although you do. It's what you have to do, but that's not my little pet phrase. Nathan, what is it? I don't like funny angles. Okay, 0 degrees is not a funny angle. 90 degrees is not a funny angle. 30 degrees is a funny angle. Anything between 0 and 90, I don't like them. I don't like it. So we got to get rid of it. Okay, Michael, you said we got to get rid of that angle, right? It's exactly what we got to do because we don't like funny angles. So let's go off to the side over here. And let's redraw that. Just the funny angle. Let's just redraw the funny angle. Here's the x component, here's the y component, here's the angle, 30 degrees, and its length is 0.38 meters per second. What I want to do is kill that 0.38 meters per second. Okay, be done with it so that I never have to see it again, never have to use it again. The way I'm going to do that is to change it into an x and a y, an x and a y, so that I have just those 0 and 90 degree angles that I'm okay with. The x component is going to be found by the cosine function because it's the adjacent side of the triangle. Cosine 30 degrees is equal to adjacent over hypotenuse. And the y component is going to be found by the sine function because it's the opposite side. Sine 30 is equal to opposite over hypotenuse. Now I can figure this one out in my head, but I don't know what this one is, the x component. You guys figure out what that one is, please. Thank you. 0.32909 meters per second. Now I want you to understand, once I've done what I just did, that 0.38 seconds is gone. It's dead to me. I never look at that again. I never want to see it again. I can, if I want, redraw this. Get rid of the 0.38. I could redraw it like this. I got, what do I have here? 0.32909 to the left, and I've got 0.19 down. And now I've got no funny angles. Now I got the one that's going up, but that's what I'm trying to find, so that's okay. I don't mind that one. I can redraw it like that or not. Doesn't matter. Let's go do what we do now. The x component, m1, let's go pi equals pf. m1 v1i plus m2 v2i equals, oh wait, what did I just do wrong? General awareness, right? We've talked about this a million times and I wasn't generally aware of this. Okay, what did I do wrong? Yep. Yeah, it's MV, right? There's one object before this explosion takes place. MV initial equals M1 V1F plus M2 V2F. Right? The guy in the skateboard were one. He was one with a skateboard before this explosion took place. Total mass is 67.7. VI is negative 0.40. M1 is 65.2. V1F, tell me what that is. Who's got V1F? X component, V1F. Who says 0.38? It's dead. You're never going to use that number again. We got rid of it. Remember, we went through that process. We thought of this phrase, I don't like funny angles. We got rid of it. We didn't like it, so we got rid of it. Don't go back to it. Bryce, what is it? We're going to make it a negative value because it's to the left. But yeah, 0.32909, right? I don't have to use the 0.38 because I've got the x component of the 0.38 plus 2.5 V2F. So we'll solve for V2F there. Let's see, 67.7 times negative 0.4. Let's add to that. We're going to add this term to it because it's subtracted on the right-hand side. 65.2 times 0.32909. No, it's going to be positive because it's negative on the right side, so we bring it to the left side by adding. And then we're going to divide that by 2.5. Negative 2.2493. So that's the x component of the green one. My final answer there. The x component of my final answer. All right, let's do y's. Get a bit of a break here. What is it? What's my break? What's my break there? Yeah. Good. The initial velocity of y, like for both of them combined, is 0. So I can just write in that whole term 0, right? Two objects afterwards, of course, m1 v1 f plus m2 v2 f. M1 was 65.2. Okay, v1f, y component. Look at what's v2f, v1f, sorry, y component. Good, excellent. Negative 0.1. Negative because it's down, and 0.19 because that was the y component of the 0.38. Did you see what we've done there? Once we got rid of that 0.38, we got the same problem that we've had for all the other ones, right? We just got x's and we just got y's, but we had to get rid of the 0.38. Anytime you see a funny angle, okay, 12 degrees is a funny angle, 17 degrees is a funny angle. Anything other than 0 or 90 or 180 or 270 is a funny angle. Get rid of it. Draw it off to the side, get the x, get the y, and then do what you do for all the questions. Put in the x where appropriate, put in the y where it's appropriate. Okay, solve for V2F there. This one's a little bit easier. Tyler, what does that work out to be exactly? 4.9. Thank you. And it's a positive value, right? Because this one went over to the left side by adding. Okay. We got negative 2.2493. We've got 4.9552. We want to find the angle and we want to find the resultant speed. All right, this half of the room, Tony Ann and over, is going to find the speed. This half of the room, Tony and over, is going to find the angle. The speed is going to be found by doing the Pythagorean theorem. And the angle is going to be found by doing the inverse tan function of opposite over adjacent. .4 meters per second, thank you. And this side of the room, who got theta? Nathan? So 66 degrees. And it would be, frame of reference is north, south, east, west, so we're going to say north, north of west, right? Okay, one of the things that we talk about sometimes when we see a problem is what makes this question similar to another one that we've seen? What makes this question different to another one that we've seen? We've seen questions a lot the same as this, right? Similar. Okay, what's similar about this question and the previous question? Question number 1 that you did for homework? It's a two-dimensional problem. There's x and y components. It's conservation of momentum. What's different about this problem? There's one big difference. And that leads to a couple other little things, but the one big difference is got a funny angle. Didn't have that in the other one. How do you deal with the funny angle? Well, turn it into a non-funny angle. Turn it into a regular angle. Turn it into one that we like. And you simply do that by going off to the side and resolving that vector. Guys, if you look at the method that we've used to solve this, in the end, it is no different than the method we used for question number 1, except what's boxed off here. Okay, this is the only difference right here. And this is grade 9 trigonometry, right? This is grade 9 math right there. All right? We've got a problem up on the board here right now where we have an explosion. The explosion takes place at the point where we have labeled X. This explosion causes an object, a 9-kilogram object, to break up into 3 pieces, 3 equal-sized, equal-mass pieces. One flies to the north at 15 meters per second. One flies to the general vicinity of southeast at 10 meters per second. Where does the third 3-kilogram piece go? All right, before we go to solve this question, what do we know for sure about where this third piece goes? What do we know for sure? The total momentum before this exploded was 0. What's the total momentum after it explodes? 0. Michael, what do we know for sure here? Should be south of west? I don't think we do know that for sure. I think we know it's got to be west. After the explosion, we've got a momentum to the west. We have to have one to the east to cancel that, right? After the explosion, we have one to the north and one to the south. Which one's bigger? We don't know for sure which way this is going to go. We know it's going to go to the west. We don't know whether it's going to go northwest like this or whether it's going to go southwest like this. My guess is it's going to go down here. But in the end, you know what? If I'm wrong, it's not the end of the world. Okay, I can still solve this question correctly even if I guessed wrong there. Its mass was 3 kilograms. Your task right now is to find the speed of this thing and the angle. All right? So I'm going to give you a few minutes to do that on your own, and then we'll take a look at it in just a few moments as a group here. All right, let's have a look now. This one says we have these 3 objects here, all equal masses, explodes, goes off in different directions here, and we have the directions of 2 of those 3 objects given to us here. We know that this is a conservation of momentum problem, right, because it's an explosion. We know that it's a 2-dimensional problem, X and Y components. Listen, I'm telling you, if you ever have more than X or Y, you have to do X and Y components. You have to. Now, in addition to doing the X and Y components here, we also have to look at that funny angle. What do we say about funny angles, Victoria? I don't like funny angles. So James, what do I do with it? Get rid of it. Let's kill that funny angle. So let's do that up here. Let's just redraw it up here. We got 30 degrees right here. We got an X, we got a Y, we got 10 meters per second. Cosine 30 degrees is equal to adjacent over hypotenuse. And sine 30 degrees is equal to opposite over hypotenuse. All right, good. Good. We could redraw that if we wanted to, but we don't have to. I'm going to now break it up into the whole thing into X and Y components. We're going to say PI is equal to PF. The initial momentum of the whole thing is 0 because it's at rest. The final momentum is M1V1F plus M2V2F plus M3V3F. Now, I don't remember if it was this class or the other class a few days ago, doing a problem similar to this, except without the funny angle. And somebody said, could I multiply M1V1F plus M2V2F and then just say P3F? Get the final momentum and then divide by the mass at the end? Could you do that? Sure you could. Okay, do it with momentum, do it with velocity, it doesn't matter. Okay, I like to do it like this, but in the end, it doesn't really matter. Masses cancel, right? How many of you caught that? How many people included the masses in their calculations? That's okay, right? You just don't need to because it's the same mass. V1F. What is V1F? What's V1F for the X component? Yep, 0. Good. What's V1F for the Y component? Tasia, what's V1F for the Y component? Sorry, V2F for the X component, I should say. 8.66. And V3F, we're going to solve for that. It works out to be negative 8.66. If we do the same thing for the y component, zero initial momentum will be equal to M1V1F plus M2V2F plus M3V3F. Masses cancel again. V1F is what? Was zero. What is it now? Justin, what's V1F now for the y component? Good. What's V2F for the y component? Derek, what's that one? V2F. Almost. Negative 5. And of course, we can solve for V3F fairly easily there, right? Get V3F, x component on the left side. Get V3F, y component, and then combine them using the Pythagorean theorem in the inverse tan function. Good? It doesn't have to be harder. It's just, once again, more work. Do the same thing you did yesterday. But now if you get a funny angle, get rid of it. Change it into a simple x and a simple y like we did there. And then go through your x components and y components just like you always do. I got one more example for you here this afternoon. You're going to work on a couple practice questions after that. And then if we have time, you will do a multiple choice question. We'll see how that goes for time, though. This one says a 19.6 kilogram curling stone. Anybody a curler here? Anybody curl? No? I've curled a few times, not very good. You pick up those curling rocks. You don't actually usually pick the curling rocks up. You usually just, you want to get over there, you slide it along the ice. They're 20 kilograms. It's 50 pounds almost. Hey, that's pretty heavy. That's a heavy rock, a 50-pound granite rock. Moving at 1.2 meters per second to the north, collides with another stationary stone off center and moves at a velocity east of north. Okay, let's draw this out before it gets too confusing. Object number 1, 19.6 kilograms, got a velocity of 1.2 meters per second to the north. Object number 2, also 19.6 kilograms, at rest. Curling rock A collides and then moves off east of north. So curling rock A is going to go up here at 12 degrees. We're calling it curling rock 1 because I don't like letters, but you call it A if you want. Where's curling rock 2 going to go? Or B? Tony, where's B going to go? Where's that second rock going to go? What's that mean? What does that mean?
I have no idea.
Sure you do. You do have an idea. You're just afraid to say because you don't want to be wrong, right? Who else knows? Okay. Yeah, it's going to go up there somewhere, right? That's exactly what you're going to say, isn't it, Tony? They both have masses of 19.6 still. Hey, we got a funny angle, 12 degrees. Let's get rid of it because we don't like funny angles. This is the angle because it's east of north, right? East of north. So it's measured from the north. Exactly the way we have it labeled there. This is X, this is Y, 12 degrees. This is 1.17. Sine 12 degrees is equal to opposite over hypotenuse. And we're going to say cosine 12 degrees is equal to adjacent over hypotenuse. You guys on this side, Tony N's side, do the sine. On Tony's side, do the cos. 4.24? 0.24? I guess it can't be 4, right? You have another couple decimal places, 0.24, 325. Okay, that's good. Ideally, you want to go to 4 or 5 decimal places, right? The y component on this side. Tony, got it? Okay, thank you. All right, now let's do x's and y's. Oh, we got a break here. We just got a break. What's the x component of object number 1? m1 v1i plus m2 v2i. What's the total x momentum? 0. Object number 2 is at rest. Object number 1 is only moving on the y-axis. m1 v1f plus m2 v2f. Oh, masses cancel too, because they're the same mass. We ever getting a break here? What's v1f? Kathleen, do you know what v1f is for the x component? Yeah, good. So deal with y's. Right. Let's deal with the y now, the y component. Pi is equal to pf, of course. This time we can't cross off object number 1, m1 v1i. We can cross off object number 2 because it's at rest. Equals m1 v1f plus m2 v2f. Masses cancel. Again, like it when that happens. Not because it makes it easier, but just because it makes it a little bit less work. v1i? Zach, what's v1i? Object number 1 for the y component. Good. 1.2 meters per second equals v1f. v1f. Tony Ann, what's v1f for the y component? Object number 1, final y component. Yes, good. 1.1444 plus v2f. I think that works out to be, take that over to the other side, we get 0.0555. Right, we can deal with this now, right? I got negative 0.24325. And we've got positive 0.0555. Now it's grade 9, right? Now it's grade 9 stuff. This time, Tony's side of the room is going to calculate this, and Tony Ann's side of the room is going to calculate the angle. The inverse 10 of opposite over adjacent. Thank you, Zach. 13.4 degrees. Should it be 3 digits? Yeah, it should. 13.4 degrees. And we're going to say that's north of west. And the hypotenuse there works out to be what, Justin? 0.25. One more digit. One more digit there, 0.25. Okay. Is that okay? Once again, what's similar about this to the other questions that we did? Oh, lots. Conservation of momentum, it's collision, it's 2 dimensions, x and y components. Everything you see up on the board, except for this, is similar. This is the only thing that's different. We got a funny angle. But when we deal with that funny angle in the little box over here, then it's just like the other questions. It's exactly the same as the other questions, conceptually. Okay? I'm going to give you a couple questions to work on here. See what you can do with those. And then we'll take a look at either of these if we need to a little bit later on, okay? All right, let's take a look at question number 1. It says a 97-kilogram hockey center stops momentarily in front of the net. He's checked from the side by 104 kilogram defenseman skating at 1.82 and bounces at 0.940. What's the velocity of the defenseman immediately after the check? I don't know about you guys. When I read questions like this, sometimes the wording of it messes me up. Like, he's checked from behind and bounces at 0.940. Who bounced at 0.940? Which one is it? Is it the hockey center or is it the defenseman that bounced at 0.940? Listen carefully to the way I read this question this time. The hockey center stops in front of the net. Who's he? The hockey center is checked by a defenseman skating at 1.2, and who's he? The hockey center bounces at 0.940, 18.5 degrees south of east. What's the velocity of the defenseman after the check? This is a collision, right? This is like two cars colliding. This is like any other conservation of momentum problem that we've done, okay? And we also know that because we have a south and an east in the same question, we have a funny angle in the same question, we know we're going to have to do x and y components. Hey, listen, if you got to do x and y components, draw a diagram, draw a picture, please. Don't skip that step, okay? I will not even touch giving you help if you're not going to draw that diagram. That is so important in these questions. We got a hockey center. We're going to call him object number 1. He's 97.0 kilograms. He's at rest. He's checked by a defenseman skating to the east. So the defenseman we're going to call object number 2. He's skating to the east at 1.82 meters per second, and he has a mass of 104 kilograms. And he, the center, that's object number 1, bounces south of east. So object number 1 is going to go down here. South of east, 18.5 degrees south of east, at 0.940 meters per second. Where do you think the other guy is going to go? The defenseman who checked him in the first place. Tyler, where do you think he's going to go? What's your best guess? We don't know for sure exactly where he goes, right? But we can take a pretty good guess. Pretty good estimate. Where's he going to go, Zach? Yeah, like up here, right? Object number 2 is going to go up here. Tyler, does that make sense? Okay, and that's what we want to find, his velocity. All right. Conservation of momentum. There's 2 dimensions. That's important. X and Y components. All that's important. No funny units here. That's good. Okay. 2 objects before, 2 objects after. 1 object hits a stationary object. So one of the momentums is 0 before the collision takes place. Oh, 18.5 degrees. Bryce, what are you thinking right now? 18.5 degrees. What do you think? What do you think of that 18.5 degrees? It's a funny angle. I don't like funny angles. Just hold on one sec, guys, okay? Don't like funny angles. So let's go off to the side. We got 18.5 degrees here. Here's X, here's Y. Listen, you can find that using cosine and sine. Who's got this X component here?
Logan Wozniak. Please
Yep.
go to Mrs. Williams' room.
Yeah. Tony, got that? Okay. And that's found by using the cosine function, right? The Y component found by using the sine function is what, Tony? 298877? 887, thank you. Listen, now we can just break it up into X and Y components. We're going to say 104 times 1.82 plus 0 equals, object number 1 is 97 times what? 0.8914? This is the big thing, right? 0.8914. Recognize that that's the number that we use right there. Plus 104 times V2F. Same deal down here, except the total initial momentum is 0. Equals 97 times negative 0.29887. Plus 104 times V2F. Remember where that, remember where this negative 0.29887 comes from? Comes from right here. Solve for V2F in both places, combine them. Guys, is that making some sense? Okay, I know, you know, we're dealing with these funny angles for the first time in physics 30, but we dealt with them in physics 20, right? We can do this in physics 30 as well. Okay, don't get bothered by it. Just deal with it the way that we're dealing with it. It's the same every time, every single time. Try question number 2 for tonight, please. Come back tomorrow with it done to the best of your ability. We'll take a look at it, and then we'll go from there. Have a good night, guys.